stage. So 20 seconds to go. Let's listen in.
T minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Nominal.
30 seconds into flight, we are feeling the rumble. We are seeing 33 out of 33 Raptor engines ignited on the Super Heavy booster.
Booster and ship, avionics, power, and telemetry nominal. Acquisition of signal, Corpus Christi.
Continuing to get good call outs. Our trajectory looking nominal, systems looking nominal. Just amazing to see all 33 lit up once again. At this point, we've already passed through max Q, that maximum dynamic pressure, and passing supersonic, so we're now moving faster than the speed of sound, getting those onboard views from the ship cameras. Now the next major milestone is going to be a hot staging maneuver. Again, we're going to be doing that in just about 90 seconds. To do that, we're going to shut down all but the 3 center Raptor engines on Super Heavy. That'll be our MECO, our most engines cut off. And then the clamps holding the 2 stages together are going to release. Starship's second stage will ignite its engines, the RVACs first, the sea levels right after that. The sea level engines will be splayed or just kind of pointed out at about a 15-degree angle. So if you look close and we get good tracking, you might be able to see those center right after. And so those 6 engines will push Starship off of the booster. All right, counting down now. We're going to be coming up right at around the 3-minute mark on that hot staging maneuver. Again, we'll see the booster engines start to shut down. You'll see all but 3 lights go out in the middle. And then we'll see the engines ignite on ship, pushing it away. And that will start carrying the ship into space. Booster will start to do its flip and then move into the boost back burn, setting it up for eventual splashdown in the Gulf of Mexico.
Stage separation. Boost back startup.
Hot staging confirmed. Boosters now making its way back, seeing 6 engines ignited on ship. Kate, we got a Starship on its way to space and a booster on the way back to the Gulf.
Oh man, I need a moment to pick my jaw up from the floor because these views are just stunning. These are live views from Starship. First stage is currently performing the
ship avionics, power, and telemetry nominal.
Good there, news informing us that the second stage or the ship, everything looking good, nominal there. First stage is currently performing the boost back burn, expecting that to last about 1 minute. That boost back burn, propels the booster back towards the coast, taking it to a landing in the waters of the Gulf of Mexico. We're only using the Super Heavy boosters, 13 center engines from here on out. As whenever they relight, you'll be able to see that in the left bottom corner. Those are the ones that can gimbal. In other words, they move and change direction in order to change the thrust to steer the first stage back to Earth. Wow, these are just incredible views coming to us. Everything is looking good for both the first stage on the left-hand side of your screen or the Super Heavy booster, as well as on the right-hand side of your screen, that is Starship, or we also refer to that as the ship. Now, the boost back burn was the first of 2 burns required to return it to Earth. The next one will be the landing burn, where all 13 center engines will initially ignite and then transition into a 3-engine burn to help slow it down. Now, just as a reminder of the Stage 1 test objectives, we're looking for controlled ascent, which we have so far. Stage separation, which, gorgeous, we cruised right through it, as well as
on a nominal trajectory.
good news there telling us that the path that Starship is on is good. Now, Starship's second stage is still firing its engines, and as you heard, following planned flight path. The ship objectives, we're looking for hot staging, again, cruised right through that. We're looking to demonstrate controlled ascent as well as orbital insertion. Now, the bottom right-hand corner of the screen shows the ship engine graphics, so be sure to keep an eye on those.
Yep, Kate, like this is just a phenomenal test so far. Super Heavy is performing beautifully today. It's on its return leg of the journey. Ship continuing to burn its 6 engines, those larger circles, the Raptor vacuum engines, the inner circles, the Raptor sea level engines. We're about 30 seconds away, just under 30 seconds away from the start of the boost back burn. Excuse me, the landing burn on the booster. You can see the grid fins rotating. Those hypersonic grid fins are guiding us through the atmosphere back towards our splashdown site. Again, we're going for a for a splashdown, a soft splashdown. So for landing burn, we're going to expect to see the 13 center engines light, rapidly bring down the booster's velocity, and then just the 3 in the center for splashdown. Let's see if that'll work. We're getting a few engines. And acquisition of signal. We'll see if we can get some other video of that. Now, this is a test objective today. It is still something that we're attempting to learn. And to make it that far, to demonstrate the controlled re-entry up to that point is pretty darn good. Ship continuing to look nominal with its ascent burn. This burn lasting about 6 minutes total. And we're expecting that this burn will end just after T+8 minutes, about a minute from now. So far, though, I mean, congrats to the team. Making it this far is a little short of the engine relight, but hey, that's something we can learn for the next one.
Yeah. Now, that view that we just had moments ago was a live shot of Star Command. There you see it again. This is our mission control center vehicle operators. Our milestone coming up is in less than a minute. At that point, ship will, or I'm sorry, actually it already has.
Starship engine cut off.
There we go. As you heard there by the call out and from the crowd behind us,
Starship nominal orbit insertion.
Starship's 6 Raptor engines have successfully shut down. We heard a call out for nominal orbital insertion, which is incredible. Look at these views, Dan.
I'm just completely blown away right now. What a day. Congratulations to the entire SpaceX team. I mean, this flight pretty much just started, but we're farther than we've had Starship, not just in space, but on its coast phase into space. Just to recap where we've come, and it's only been 9.5 minutes. How has it only been 9.5 minutes? We lifted off right on time at 8:25 and have to hold all 6 engines boost back burn. And then we did make it all the way to the landing burn this time. Didn't light all the engines that we expected, and we did lose the booster. We'll have to go through the data to figure out exactly what happened, obviously. So be on the lookout for information about that. But wow, a ship in space. We've got a bunch of, as we said, ambitious objectives ahead of us over the next couple of minutes and pretty much over the next hour, where we're going to really, we've got the ship in space. We're now going to take advantage of this and try and learn as much as possible about some of the other systems, including that first ever Raptor relight in space. So it's just going to be incredible. So all of that still to come. The mission just started, but wow, what a liftoff! What a hot stage! What an amazing sight to see Starship there in outer space.
Breeds innovation. This is what I've come to learn from the rich history of Japan as an unsung player in the space race. From launching the smallest orbital rockets in the world, to the most advanced research laboratory in space, to the future of asteroid mining, Japan has taken a unique path through the decades of interstellar innovation. This is the story of Japanese space exploration. The Japanese Aerospace Exploration Agency, or JAXA as we know it today, is actually a development, having only been founded in the year 2003, but you might not know that the Japanese nation has been involved in space exploration since the mid-1950s. Prior to JAXA, there were actually 3 separate Japanese space programs: Japan's Institute of Space and Astronautical Science, the National Aerospace Laboratory of Japan, and the National Space Development Agency of Japan. The 3 institutions merged in 2003 to secure more concentrated funding for space exploration from the Japanese government, and so that space exploration efforts could be more centralized and organized. Where we really need to begin this story is in post-World War II Japan. As part of their submission to the United States, Japan is now prohibited from developing any new technology that could be associated with military use, which of course covers most of the technology involved with space exploration. In spite of this limitation though, Japan is able to press forward in their own way, and by the mid-50s they have the beginnings of a space research program. The Institute of Space and Astronautical Science started off as a research group from the Institute of Industrial Science at the University of Tokyo. This group was led by Hideo Itokawa, a man considered today as the father of Japan's space development by Japanese media. Around the same time, the political landscape of the world is changing fast. The United States becomes much more concerned about the nuclear threat of the Soviet Union. They amend the Japanese military restrictions to allow for a self-defense-based armed forces. The remaining caveat is that Japan is still prohibited from developing offensive weapons technology. Essentially, what this comes down to is that the Japanese can't make a ballistic missile, but they can make an unguided rocket. This is where the Institute of Space and Astronautical Science really comes into their own. They start by developing miniature solid-fueled rockets. Their first design is known as the pencil rocket, not only because of the resemblance in shape, but also in size. This rocket is just 1.8 centimeters in diameter by 23 centimeters in length. It's basically the same model rocket that you can buy at any hobby store today, but for the Japanese in 1955, this was one small step towards greatness. Next up was the baby rocket. Compared to the pencil, it was gigantic, but still only reached 8 centimeters in diameter and 120 centimeters in length, though it was big enough to carry a few scientific instruments into the sky, which was another important step towards the future. This quickly led to the development of the Kappa systems of sounding rockets. These are solid-fueled rockets that are used for probing the upper regions of Earth's atmosphere. The Japanese were hoping for an altitude between 60 and 100 kilometers, which would take their instrument payload right up to the edge of space. It took a few attempts to get things right. Many of the first Kappa designs simply exploded on ignition. The first truly successful design was Kappa 6, now 25 centimeters in diameter and 5.4 meters in length. Using a new composite-type solid propellant, the K6 was able to reach an altitude of 60 kilometers in the year 1958. You might notice that these rockets are always launched at an angle. We'll get into that in just a bit. The early program culminated with the launch of Kappa 8, now 40 centimeters in diameter and 11 meters long. The two-stage sounding rocket carried a scientific payload all the way into outer space, reaching 160 kilometers in altitude. In September 1960, a scientific payload on the K-8 rocket succeeded in observing the Earth's ionosphere and took the first ever density measurement at that altitude. The world was starting to take notice of what Japan had accomplished. As the space race of the 1960s kicks into high gear, the American and Soviet programs become laser-focused on crewed spaceflight and satellite deployment, each nation constantly pushing towards bigger and more daring milestones. Meanwhile, the Japanese embrace the limitations of their own space program and make scientific research and observation in the upper atmosphere their main focus. Japan's next major development is the Lambda series of rockets. They were essentially just a scaled-up version of the solid propellant sounding rockets, now just a bit less than 1 meter wide and around 16 meters long, but they had the capability to reach high into the outer atmosphere and even deploy a payload into Earth orbit. By 1965, a Lambda 3 rocket had reached beyond 1,000 kilometers in altitude, and in 1966, the Lambda 4S was ready to attempt Japan's first ever satellite deployment. You might notice here that the Japanese were still launching their orbital rockets at a diagonal angle from the ground, while the Soviets and Americans have been pointing their rockets straight up. So, what's the deal with that? It all comes back to Japan's limitations under the post-war constitution. No offensive weapon technology means no guidance system on their rockets. So, while the Lambda rocket is essentially a surface-to-air missile that can reach all the way to outer space, it has to get there on one set flight path. So a typical rocket will launch straight up into the air for a few seconds, and then the guidance system will begin to steer it over into an arc-shaped trajectory. The Japanese engineers compensated for this by simply pointing their rocket diagonally from the ground so that it would naturally achieve the same arch without the need for steering in flight. Then at high altitude, when the atmosphere thins out, the Lambda's side fins are no longer effective, so another system fires to put the rocket into a spin of 2 rotations per second. This keeps it stable through the flight. By slowing down and speeding rotation, the rocket payload can be maneuvered to an orbital insertion. Now, that's not to say that everything came easily for the Japanese space program. It took 4 failed attempts at deploying a satellite until they finally achieved orbit with a 24-kilogram satellite payload named Osumi in the year 1970. This made Japan the 4th nation to successfully deploy an orbital satellite. The Soviet Union was first, followed by the United States, and France was the 3rd nation in 1965, which is news to me. Did you know that? Being disassociated from the cutthroat competition of the space race left Japan with a unique opportunity to focus their efforts entirely on space science and research projects. Over the decades that followed, Japanese scientists would go deep into the study of atmospheric science, weather and climate patterns, magnetic fields, and X-ray astronomy. These missions were powered by the M-series of orbital rockets, again, just scaled-up versions of the early solid propellant-sounding rockets, and yes, they still launched at an angle. The 1980s brought a new wave of accomplishment for Japan's space program. Sakigake, or Pathfinder, and its twin vehicle Suisei, or Comet, were Japan's first spacecraft to escape Earth's gravity. Launched in 1985, they also became the first deep space probes to be deployed by any country other than the USA or the Soviet Union. The Pathfinder and Comet would be one of many spacecraft to study Halley's Comet as it cut through the inner solar system in 1986. Unfortunately for Japan, the early 1990s marked a time of great economic struggle, something often referred to as the lost decade. But the country's outer space operations were able to come back in a big way with the International Space Station project. Behind the United States and Russia, Japan made the largest contribution to the ISS with their Kaibo or HOPE module. This 3-part research outpost would become the single largest module of the ISS and the most advanced scientific laboratory in outer space. The main pressurized module contains 10 scientific experiment racks that have been used to study everything from cell biology and microgravity to the environment of outer space, the composition of Earth's atmosphere, global weather patterns, cosmic rays, and laser communications. The little top hat above the main lab is called the logistics module. It's basically just pressurized storage space. The exposed facility is a really fascinating aspect of the Kaibo lab. This is also known as the terrace, and it's located on the outside of the main module. It's essentially a big shelf where you can place experiments that will be completely exposed to the environment of outer space, and these experiments can be managed by Kaibo's own 10-meter robotic arm system, but there's also an airlock on the pressurized module that allows astronauts to spacewalk out onto the terrace and manage the experiments. The Kaibo module also has the ability to deploy very small cube satellites, so instead of having to launch your instrument directly into space, you can ship it to the ISS and the Japanese can fire it out into orbit. Another largely unsung contribution Japan made to the ISS was their HTV supply ship. This would carry over 5 metric tons of pressurized cargo and 1 ton of unpressurized cargo to the ISS, and would often be used to remove as much as 6 tons of waste. The HTV was launched using a new rocket from JAXA, the H-2. This rocket was a very big deal for the Japanese space program. A liquid hydrogen-fueled medium-lift vehicle designed and manufactured in Japan by Mitsubishi Heavy Industries. With up to 4 strap-on side boosters, the H-2B had the highest power-to-weight ratio of any orbital rocket, and this one launched pointing straight up. Now, you've probably heard this said before, that the first trillionaire will be the person who figures out how to mine an asteroid. If there's any leader in the field of extracting new resources from asteroids, then it's Japan. Continuing on the trend of embracing limitations, the Japanese didn't choose to pursue crewed spaceflight, or Mars rovers, or moon bases, or any of those flashy projects, but they did put the nation's significant expertise in the field of robotics to use in their space program. The Hayabusa, or Peregrine Falcon, was the first vehicle to touch an asteroid and return home with a sample. The mission was launched in 2005 on a Japanese M-series rocket. It blasted off on a signature diagonal angle and made it all the way out to the near-Earth asteroid Itokawa, picked up a handful of dust from the surface, and then made it all the way back again in 2010. The spacecraft was intended to deploy a secondary robotic lander named Minerva, but it missed. Since the gravitational attraction of an asteroid is so weak, it's actually pretty difficult to land on. It's not very sticky, so with a slight misfire during the rover deployment, it didn't stick and it just kind of floated off into space. And then only a few years later, in 2014, Japan went even bigger with the Hayabusa 2 mission. This larger payload was deployed on an H-2 rocket with a destination on the near-Earth asteroid Ryugu, a carbonaceous asteroid that is thought to preserve ancient material left over from the era when the solar system was formed. Not only was this mission a second attempt at retrieving material from the surface of an asteroid, it was also a second chance at leaving behind a rover, and this time, it was successful on all levels. The Minerva 2 payload actually carried 2 individual robots named Hibu and Owl, which is weird because Hibu means owl in French. Either way, these aren't rovers like you've seen before, they're more like metal boxes that hop around on the surface of the asteroid. Since the asteroid has such a low force of gravity, it doesn't take much energy to fight against that pull, so all they had to do was rotate a mass inside the rover's body, and that torque would be enough to make the robot hop forward. And it's thanks to the Minerva robots that we have this, the first pictures ever taken from the surface of an asteroid. In the future, the Japanese space program has plans to leverage their asteroid sample technology to complete the first ever touchdown and return from Phobos, one of the 2 moons of Mars. Since Mars is a relatively small planet, it also has relatively small moons that are more like asteroids. The plan is to launch the Martian Moons Exploration Robotic Space Probe in 2026 on JAXA's latest H-3 rocket to the Mars system. On arrival to Phobos, the spacecraft will make at least 1, but possibly 2 landings on the surface to retrieve at least 10 grams of sample material. From there, the probe will move on to the second moon of Mars, Deimos, where it will conduct an orbital observation before sending a return module back to the Earth, where it is scheduled to arrive by 2031. This might not be as thorough or in-depth of a mission as something like NASA's own Mars sample return, but the Japanese has twice proven to be effective, so it's much more likely to be successful and will return the material to Earth much sooner, which ends up being a pretty solid metaphor for the Japanese approach to space. They are not trying to be the biggest or the best operation in town, but they are effective at getting the job done and putting science and discovery on a higher priority than planting flags and winning races.